Good morning, everybody, and welcome to Big Tech Day 25. Here are the speakers of the first talk, Valentino, Golob, Lukas Rammelmüller, and Andreas Dirscherl. They asked me to save your questions for the Q&A right after the talk. I'll be passing around this one microphone then, so raise your hands then. And I'll introduce them a bit more now. Lukas and Valentino are senior consultants at TNG with backgrounds in physics and mechanical and computational engineering respectively. Both now specialize in platform engineering and Kubernetes cluster operations on the cloud and on bare metal. Lukas is involved in TNG internal GPU cluster for the AI purposes as well, and Valentino drives the ever important security topics, I heard. Andreas is Director of Engineering at Idgard, and as part of a strategic data center initiative, he developed the cloud-native operator-secure bare metal Kubernetes stack for the patented sealed cloud. Andreas combines deep technical expertise and business acumen, fostering a culture of excellence, sustainability, and agile development. Enjoy the talk with these three amazing speakers.
Hello, good morning. So let's start by Idgard. So because it's part of the title, it's a product, it's a SaaS application, it's for file collaboration, secure, and also for data store and also for collaboration. So it's about, for the users, it's a product where they can store their files, PDFs, create data rooms, work together, and store them, everything. The main topic there, it's a high secure data platform, and what we see also for the high security, makes the next slide, is that we have everything running on the sealed cloud, and here we have the high secure topic on the outside world, so the normal, the hackers, the stuff like, you know, but this is like, there's a lot of practice, everybody knows we do here the stuff, but we have another point of secure, it means, oh sorry, it's here, it's our own employees, and we as a company. So because half of the attacks are gone by, maybe we forgot some admin passwords to reset or some to change, to harden, and then after some years you find a server with a root password 1, 2, 3, 4, because it was forgotten. And just here, this is an important topic for us in the C cloud, and it means that we have a zero trust approach, that we as a company and our employees never have access to the data of the customer. And just here also from operating system point of view, that's not easy. Because if you have access as root, you can do a memory dump, in the memory some passwords finding, and then it's gone. So that means we have to secure everything, memory, runtime, CPU, everywhere where we have the unencrypted data of the customer. So storing on disk is easy. We encrypt before. On the disk, nobody can read it, but just in the runtime. That's an important topic here. And we have everything running on our C cloud. And in the past, then we decided in 2021 to give them an upgrade. Because in the past, it was like together, like OS system, bare metal, application software was just one build, and we just deployed them on the machines, but it's hard then to maintain the software, to update the software, and also to maintain the full stack. And with a lot of so just was one thing was every deployment has a downtime. So then we had the topic that we want to modernize the platform to improve scalability, maintainability, and continuous delivery, and just with one big requirement that we don't have access. This is just our major requirement for everything what we do in this company, and that also was the major requirement for creating a new platform for hosting our software. So, and here I give to my colleagues at this time from TNG to explain the technical points.
Right. Thanks, Andy. Does this work? Yeah, now it works. Thanks, Andy, for showing Idgard from the business perspective. Now, let's have a look at the technical side of things. And the first question that we need to answer is, what does zero access even mean? Or in other words, where do we need to secure our data? There's a few places that we have to consider. First thing is in transit. So anytime data goes over the network, we need to make sure that nobody can get access. Typical attacks here are man in the middle, eavesdropping, or packet tampering. This is something that we see on a daily basis, right? Whenever we interact with a website or anything, we have encryption. So it's fairly standard practice, and this is relatively easy to implement, so we don't have to worry too much about it. The second thing is at rest. So whenever data is just sitting around, we need to make sure that it's encrypted. Think databases, S3 buckets, or even your persistent volumes in Kubernetes. Luckily, all of those things are pretty easy to implement too. Those technologies typically involve out-of-the-box support for that, and we don't have to worry too much. We think, for instance, S3 buckets that are encrypted on Amazon. So one common misconception, though, is that data at rest encryption also includes in-use protection or runtime protection. But it's a totally different thing. And the problem here is that operating on the data requires plain text. So we need to decrypt the data to operate on it. And this is very hard to ensure ourselves against. So this doesn't have any easy solution. Andy already mentioned it. This is the core thing that Idgard does. Typical attacks are, for instance, if tenants that are on the same machine scrape memory or have a swap leakage and things like that, or access to machines in general where the data operation happens. This is not really easy to do, as I mentioned. If you remember, Microsoft a few years ago had a leak of some very prominent security key. That was because of a memory dump, so even the big companies don't struggle with that. What can we do to ensure against ourselves these attacks? First of all, well, we need to make sure that nobody accesses the servers. Well, that's, I guess, true for any cloud deployment. We need to make sure that also nobody can physically attach it, and we have to have pretty good workload isolation. But the thing is, it's hard to do only from an infrastructure perspective. We also need support from the app, so some app-level logic, in our case for Idgard, needs to be done in order to make proper use of that. And the last thing, Andy already mentioned that, is operational safety. So how do we avoid to have access for the people that actually set up the system and keep the show running? And this is very challenging to do, almost impossible. The tech words here are zero trust architecture, so we trust no actor and no piece of infrastructure by default. Principle of least privilege, so we don't give more access as is strictly needed. But even and also things like, and even if there is manual interaction, we need to have a strong 4ICE principle and automate as much as possible in order to avoid that people access anything and abuse it. But it's very hard to do that, and there's no 100% guarantee that if you have the control to configure the system that you actually don't have access. What you can do is we have a proper auditing system in place so that if anything happens, you're alerted quickly and you can react quickly. As mentioned, those 2 points are part of the patented Seal Cloud technology that Andy already mentioned already, and it's going to be the rest of the talk that we are diving into that. All right, so with these fairly steep security requirements, I think it's clear by now, and also, I guess, from the talk title, that the cloud is out of the picture. So what it leaves with us is on-premise or co-location. So we buy a bunch of servers, we bring them to the data center. It doesn't have to be, your own garage or your own basement. Any sufficiently secure data center will do. You just have to make sure that nobody can access your servers. That's logically over the network or even physically. And the first thing you do when you come to the data center is you set up the network. We'll leave that out for today. That's an entire talk on its own right. If you want to know more about it, I'm sure Andy is happy to chat later over coffee. There's a lot of things to be said about that. But for now, let's just assume that these machines are properly set up. They can talk to each other. So what's the next thing that we need to address? We need to think about how do we operate the app and the infrastructure. And what's the goal? The goal is, in the end, we want to have an app that is resilient, secure, and we don't want to have a lot of operational overhead. Well, this is a Distributed setup, right? Distributed computing. So this task is not an easy task, and regardless of which framework you will use, it's not going to be easy. There's always going to be a lot of complexity. But as you might have guessed from the talk title, and I guess it's also part of the reason you're here, well, we use Kubernetes for that. And so in a nutshell, what's Kubernetes? Or what's important from Kubernetes for us today? It's a container orchestration workload, container orchestration framework that takes care for deploying applications for us in a declarative way. And declarative means we just tell it, hey, I want this app deployed with this type of resources 3 times. And Kubernetes does that for us. We don't care how it's done. It just makes sure that's there. And the most important thing is also cares if something breaks, it will fix itself, ideally. That's very convenient for applications, but also for infrastructure. So we don't have to do any special setup for instance, our monitoring stack and other things. So we can just use the same logic and the same way to provision that, which is a quite convenient feature. Over time, Kubernetes has become the de facto standard for operations like this, also at this low level that you have with bare metal Kubernetes. And why? Because it does abstract away a lot of the complexities for us. So we still have to take care of them, and we still need to understand it. But things like networking are becoming easier, security, it's all in one concept. So there is one framework that covers all of that, rather than having a multitude of tools that we would have to understand and take care about. Of course, there's people that say, well, Kubernetes is way too complex, you ain't gonna need it. And yes, it's true, but from my perspective, and I guess also the reason why we choose this technology is it's actually the simplest way to operate such a stack. Now, a fair question is, why don't you use any of these fancy UI tools where you can click and then you have a cluster and you're done? And yes, true, they do have merit. A lot of them use virtualization, so they are based on virtual machines. And the most problem for the setup that we're talking about here is that they have an agent installed. And this is against the security policy that we had at Idgard, so we cannot have agents that we do not control. So these solutions are out of the picture. All right, so our servers just got an upgrade. We decided that we now have Kubernetes. That's our way to go. So do we go now to the data center, plug in the USB stick, and then say, okay, cool, let's install Kubernetes? Well, no, it's a bit more complex than that. Basically, what we're doing, we have to build our own cloud, right? So if you think of a managed Kubernetes service, what you do is you go to some UI, or you use Terraform, or whatever your favorite infrastructure provisioning tool is. You say, okay, I need 5 nodes, make 3 of them master nodes, and I have 2 for workloads. Some magic happens, and what you can do is you interact via the API. Well, you have deployments, resources. If you're fancy, you do auto-scaling, but that's about it. So this can be complex, and you still need to know what you're doing. But if you're operating the stack yourself and you have the machines yourself, all of this automation, nobody's going to do it for you. So you have to do the magic behind the hyperscalers yourself. And what are the things that we need to consider here? Well, I mentioned networking is one thing. Although there's a network team, cluster networking is still something that needs to be addressed. Storage, always an issue. Kubernetes best done with stateless applications, but sometimes we do require storage, so we need solutions for that. A thing that is often forgotten is public key infrastructure. So we need to make sure that the pieces that talk to each other do that in a secure way. And it's often the case that keys are not rotated or stored insecurely, things like that. So this infrastructure is something that is really something we need to take care about. Something as banal as upgrades. If you have very little control over your servers, this becomes tricky relatively quickly. And also, you need to really take care about it because nobody will tell you do this. And one thing that is really out of the picture for many people is cluster formation itself. So I mentioned when you go to the UI and you say, I want this cluster and you want that many nodes, things happen and they're there. However, if you do this yourself, you need to find a way how the machines that you just put to the data center actually become nodes in your Kubernetes cluster. And this is something that requires a lot of thought, and we will hear more about that in just a few minutes. So, first learning of the day, only do this if you have a good use case. Why? It is operational overhead. It requires time and effort, and not just a one-off. This requires constant effort. So the use case better be good. One of the use cases that we found that was good was we needed the command of the chain of trust, and we needed data sovereignty. There might be others, I'm sure there are, but this is really something that you don't, decide lightly. Well, that being said, for all of these low-level things that we just mentioned, there's a lot of tools available that help, right? For network, there's nice container plugins like Cilium. For storage, a standard solution, for instance, is Longhorn. So there is a lot of open source tooling, like Kubernetes itself, that help, that have a good community, and that are maintained well. And they can also be run in a relatively maintenance-free way. Even for the cluster formation, these days, there's a new technology coming out. For instance, Gardener, maybe some of you heard about it, or Metal Stack. So these are ways to provision a bunch of clusters, also on bare metal, and have a relatively quick cluster setup. The problem why we decided against those is either they were too immature at the time we started, or again, the same problem that we had with the agents for the nice high-level tools, because we don't want to have an agent running. All right, so, well, I think we know that bare metal Kubernetes is challenging, and you better have a good reason for it. Do we now go to the data center and install Kubernetes with our USB stick? I think not. Before we do that, we have to face a few decisions. There's a few more than these three, but those three are the ones that we will talk about more today. So the first thing is cluster topology. So how do your security requirements shape the form of your clusters? So basically, which workloads runs where, and how can we isolate them? Or in other words, we have to find the right trust zones. The second thing is the deployment itself. I just mentioned it, the cluster provisioning. So how can we provision hundreds of clusters in a way that is reliable, resilient, secure, and most of all, maintenance low. I won't say maintenance free. And the last thing is we need a proper base platform for that. So operating system that supports all that, Kubernetes distribution that is hardened and able to be hardened properly, and ideally all of this is open source and well maintained. And for that, Valentino will show you the details.
Thanks, Lukas. So what we will continue with now is we will first find out the sensitivity level of the workloads that we are having. Then we will see how this influenced our security requirements. And then we will see how this shaped, at the end, our cluster topology. But first, I want to give you like a quick overview on the different services that we have in our cluster. So the first one is Idgard. And Idgard, at the end, is the one and only place where we have unencrypted customer data. Then we have the database workloads. And here we have encrypted customer data. And then we have other supporting services like Keycloak, which is our identity management system, HashiCorp Vault, which is our secret management system, and Crossplane, which is basically some sort of Kubernetes native infrastructure as code tool, which we use to configure Keycloak and HashiCorp Vault. So the next thing that we will do is we will now classify the workloads by the sensitivity level of data which they are holding. So first, we have medium sensitive services. And here, for example, you see that the database is classified as this. So why is the database classified as medium? Because the database is encrypted both on storage level and also on row level by the application itself. So this implies for us that even if you have a database admin user with access to your database, the person cannot read the data. So this is why it's classified as medium. Then we have high classified services like Keycloak, HashiCorp Vault, and Crossplane. Why Crossplane? Because Crossplane configures the secret management system and the identity management system. So if a person would gain access to Crossplane, then the person could misconfigure your identity management system and secret management system. And then we have the Idgard service itself, and protecting this is for us like the highest priority. right? This, again, one and only place where we have unencrypted customer data. Oh, that was a fast switch. Okay, so now we know the classification of the sensitivity level of the workloads that we have. And for the high and highest classified services, we disable the SSH access for the servers where their workload are running on. So this means like nobody has remote access to those servers. And additionally, for the Idgard workload, we also do not have, the servers do not have any persistent storage, right? The servers only have RAM. So if the servers are powered off, then all of the data is gone. Okay, so now we some sort of have our trust boundaries, and we know what we want to separate from each other. So the next question is now, how do we separate it from each other? And the first option that we have is that we just run all of the workloads in one big physical Kubernetes cluster. And then you separate the trust boundaries using Kubernetes logic. So what you need to take care of is, for example, node isolation. You need to make sure that high and highest classified workloads only run on servers that have the SSH access disabled. Or you need to take care of network segmentation between the trust boundaries. And all of this requires quite some complex configuration that also can be misconfigured, right? To do this properly, this needs to be done good. So we have thought about something else. So what about if we just separate the trust boundaries by using dedicated physical Kubernetes clusters? And with this approach, we are basically isolating our different workloads with different sensitivity levels by design, without the need of like any complex Kubernetes configuration. So you have benefits like that you have lower operational risk, right? Because it allows for misconfiguration. Let's assume someone misconfigures your access control in the stateful cluster, then your stateless cluster or the other cluster, they will not be affected. Another benefit is that you have like true physical network segmentation. So you can really put firewalls now between your different trust boundaries. And another benefit is then that you are minimizing the blast radius. So let's say you have a security breach again in the stateful cluster, then it's way harder now for the security breach to spread across these trust boundaries. Okay, and this multi-cluster architecture is also what we ultimately implemented. So what we are doing is we are basically separating now the trust boundaries, which is the red line, using physical infrastructure boundaries. So far we have solved like our cluster topology, how this will look like. So we'll now go to the next challenge, which is how do we now install the OS system on the server, right? Because we have like hundreds of servers, and how do we boot the server? Because visiting like a data center, for example, with an USB stick and then just manually installing, all of this is first very impractical at scale. Second, such an operational user is not allowed in our case. And to be fair, like nowadays, probably nobody would do this manually anyways. But also remote server management tools that you could use, for example, to install like an OS system over the network, they are prohibited in our case. The only thing that we can do is powering off and powering on servers. So our solution for this is to boot the servers over the network. And at a very high level, what this means is that you are powering on a server, right? This we are allowed to do. And then the server pulls the operating system. I will check. Okay, so on a very high level, how this looks like is we power on the server, then the server pulls the operating system from some central source, which is here, which is under our control, right? We trust this, and then the server installs the operating system. Okay, so this means our current state is that we have servers that have an operating system installed, and which are booted, right? They are powered on now. But to make like a server now really functional, it also, so really functional in the sense of that at a later point it can join our Kubernetes clusters, it also requires some configuration, right? So we said we have database servers, they need to have their disk partitioned. We also said that we have some servers where the SSH access is disabled. So we need to disable the SSH access for those servers. Or just like network configuration of the servers. All of this configuration we still need to do. So remember, SSH access is disabled. So for us, traditional push-based configuration management tools, they won't work. So what about if we think about it differently and we just flip the model and try to achieve some sort of pull-based GitOps-driven approach? So what do I mean with that? Our goal is there that that we have Git as our single source of truth now for everything. So not only for application code, but also now for the server configuration. And then the second part is, right, we said we do not want anyone to push the configuration to our servers, but what we now want is that the server itself, it pulls the configuration from some central source, and then it self-configures itself. And what we are achieving with this is that we have a full audit trail and also a review process, because we are tracking then everything via Git, right? Also our server configuration. So at the end, we know who did what, when, why, and who approved this. Okay, so we now know that this is our goal. So how did we achieve this? We used Ignition as our provisioning engine for this. So this is like the engine that configures the server. And Fedora CoreOS as an operating system that integrates, that supports Ignition. And what I will now show you on a high level is how this server provisioning looks like. So first, we power on our server. Then, at some point during the boot of the server, Ignition will start. So Ignition runs in the init ramfs, and you can think of the init ramfs as some sort of bootstrap mechanism to get the real operating system up and running. Okay, so Ignition starts. Then Ignition pulls the server configuration from a central source, and then Ignition uses this server configuration to configure the server, right? So again, configures the network, partitions the disks, disables the SSH access, and it just configures like any service that is required so that at a later point it can join the Kubernetes cluster. So let's say Ignition did its job. Then the end result is that we have a fully configured operating system and a server that joined the cluster. And there's like one point that I want to highlight again, and it is that Ignition only runs during the boot, right? If the server is up and running, then there is no Ignition anymore. And this means that Ignition encourages us to use immutable infrastructure. So we are somehow forced to treat our servers as cattle and not pets. So this means if our server is broken, then we do not access the server and fix it, but what we are instead doing, we are replacing the servers. So as an example, let's say we need a change in our server configuration. What we are doing is we are updating the server configuration in the central source, and then we are just restarting the server. Then Ignition runs again, pulls the configuration, configures the server according to the new configuration, and the server joins the cluster again. And this is on a high level how our server configuration looks like. But Ignition support is not the only reason why we decided to use Fedora CoreOS. There are also other benefits, like for example that it has an immutable file system, so it avoids configuration drift. Another big benefit is that it is container optimized, right? So this means it has a minimal footprint. At the end, the operating system just comes with enough components so that you can run containers, which is a requirement if you want to have a Kubernetes cluster. And this means at the end that you are minimizing your attack surface with it, because you are not installing like any unnecessary services or packages or daemons that potentially could introduce security vulnerabilities into your operating system. And there are also two other benefits that are important, like because of our special boundary conditions that we have. The first one is Fedora CoreOS can run entirely from RAM, right? Remember, we have disk class servers, so we need support for that, and also it supports a network boot. But Fedora CoreOS is not the only operating system that supports Ignition. There are also alternatives like Flatcar, Red Hat CoreOS, or MicroOS by OpenSUSE. Back then, we decided to use Fedora CoreOS because we saw like a strong community. It was well documented. It's open source, so we went with it. Okay, so let's recap what we have established so far. So we know our cluster topology. We have solved the server provisioning challenge using network boot and Ignition with Fedora CoreOS. And now we will come to the next layer, which is the Kubernetes deployment itself. The thing is, Kubernetes is not Kubernetes. So there are multiple different flavors of Kubernetes out there. There's, for example, vanilla Kubernetes, which is basically the basic and pure form of Kubernetes without any add-ons. And this is like very flexible and customizable, but it requires quite some configuration. And to be fair, it's probably quite fun to install and operate your cluster like this. But in practice, most of the people just don't have the time to do it like this. So what most teams do is they use something called a Kubernetes distribution. And a Kubernetes distribution is just some sort of packaged version of this basic form of vanilla Kubernetes that comes with some additional functionalities. And these additional add-ons, they have the goal to simplify your installation, your operation, and your configuration of your Kubernetes cluster. The thing is now that there are like multiple different versions of Kubernetes distributions out there. This, for example, is a list of 68 different Kubernetes distros that are currently certified by the Cloud Native Computing Foundation. So the question that we now have is, which one should we use? Luckily, our requirements are quite clear, right? We know that we have to run it on bare metal. We are not allowed to run in the cloud. And we want a secure one. And this is where RKE2 is a good fit. So yeah, let me explain to you what RKE2 is. It's an open source Kubernetes distribution by Rancher. And additionally, to simplifying like the installation, the configuration, and the operation of your Kubernetes cluster, it is also hardened by default. So what does hardened by default mean? It means that it passes like the majority of the CIS benchmarks without any modification. And the remainder of those benchmarks, they are like host level settings that RKE2 cannot modify. But if you want to pass like all of the benchmarks, then you need to change those host level settings. And for example, if you want to do that, you could use Ignition for that, right? Because it's like a low-level utility that can do this. So I talked about CIS benchmarks. CIS stands for Center for Internet Security. And those benchmarks, they are basically some sort of security guideline that have been specifically developed for Kubernetes. So you can think of it as some sort of security checklist for your Kubernetes cluster. Okay, so let's recap again. We have established our cluster topology. We solved the server provisioning challenge. And now we do not only have a Kubernetes distribution that like simplifies our operation of the Kubernetes cluster, but we also have one that meets our security demands. And as a result, what we now have is we have like a self-hosted bare metal cluster that just feels like a managed one. So now the developers, they can just come to our cluster and deploy their applications on it, how they are used to do it. Yeah, Lucas, back to you.
Thank you. It's not quite like a managed cluster, I would say. There are still some special operational challenges that we need to address in such a restricted setup. That's the last point that we want to talk about today. The first thing, lifecycle management. We already heard the app itself that we want to host is running on immutable infrastructure, so we don't have any access there. We cannot just configure something on the fly, so reconfiguring requires reboot. First of all, that's hard to do without proper scripting if you have a bunch of servers to do that, and no management interface to do. We only have the power switch. So not only does your setup have to support this, but also the app itself needs to support just being killed out of nowhere. And second of all, if anything goes wrong with an upgrade, it's very tough to troubleshoot that because we don't have any logs right from the beginning, so boot logs will be hard to come by, and this is something that we need to think about how to implement. The second thing is network configuration. Yes, again, the network. So that's done by a different team, and it's industry standard that this is mostly not done by infrastructure as code. And we heard before that all the configuration we had was infrastructure as code or GitOps driven. So those two things do operate on a different time scale. So changes in the cluster setup is quicker than changes in the network setup, and there's some friction. Also, handovers between the teams is always a bit of a challenge, because it's very hard to configure these clusters without actually also thinking about the network isolation, like VLANs and stuff like that. Aside from the bare metal details, there's things that any Kubernetes cluster has to consider. And one thing here is access versus security. We heard the SSH is disabled, which is great for security, terrible for troubleshooting though, because if you want to check if your disk does some weird stuff, you need to have some access. The same goes for kubectl exec. So if you want to exec into our containers because the app is doing some funky stuff, it would be nice to have. Well, we don't have it. And the way to solve this is to invest properly in good observability, because that would, in the first place, require you to not have access if everything is already in your observability tool. This is something that becomes especially important in this restricted setup. If access is needed at some point, and can never be ruled out, of course not to the decrypted customer data, but for instance to the central cluster that we had, what helps is self-service. So also roll out the permission strategy with GitOps and have a proper review process in place so that the important people, such as Andy, have to say, okay, cool, you have access, and you get access for an hour so that it can be revoked really quickly. And even though that all of these access and security permissions are done with GitOps, there's a lot of complexity because there's a bunch of tools involved, for instance, Argo CD and, I don't know, HashiCorp Vault, Kubernetes itself. Any solution that requires some access requires also its own configuration. And since we have to build all this fancy cloud stuff ourselves, we don't have a central identity management system. So we need to do this ourselves as well. And this becomes confusing quite quickly. So what we can do here is, again, proper review process, and we have to validate it in the pipeline. So whenever something happens, we have to check, okay, cool, is this a valid configuration? Does it give too much permissions? And also we need to observe for the live system who has access to what, in order to make sure that there's no unwanted access around. Of course, there's a few more things to consider, and we're happy to take questions and chat. But for now, that's our story of the bare metal Kubernetes setup at Idgard. Back to you, Andy, for a wrap-up.
So, thank you both. Very nice presentation about the technical stuff. So, and I was thinking, what should I bring you to the end? So, a lot of benefits, but we have it Kubernetes, but you can also find this in the internet. We can have a talk later, but then I was thinking maybe the best thing is to show like what you need for to having this by your own. So how much people, how long it takes, like a little bit of overview, because this is something we don't know maybe on this time, because some of you maybe or some in the past I also used AWS. You don't know how much real cost you have. You see maybe it's cheap, but I can promise you AWS is not cheap. It's just easy. That's the topic. It's easy for you, but it's not cheaper than doing by yourself. And this I want to show. So how long it takes to set up the full platform. So starting by greenfield 0 up to have our SaaS product migrated and up and running. And it takes like from March 2020 to November 23. So it's just 1 year and 1 month or 2 months. And the development time was just 1 year. And the amount of people that works here was 6. So we had 6 platform engineers. And also important, they are not from Silicon Valley and studied 20 years or working 20 years for AWS and something like that. So there was just a lot of juniors, some seniors, but just normal skilled people. So you don't need to think about where I can get people for that. You find them. You find them in Munich, you find them in Germany, in every country. So it's not a problem. So 6 people, 1 year, and you have your own platform. And now what we have now is a really fast turn to market, means if our software development has a new product, a new app, and it's deployable in 1 day by ourselves in our infrastructure, without having a multi-cloud, hybrid cloud easy or something else. And the operating now, it's 4 people, because this 2 was still for developing, but now we are at 4 people for maintaining 200 servers with a lot of pods. I think it's a few hundred different pods from the software part of view, and it's just running. So just to give you the ramp up, it's easy. You just need to do it. Cool.
What great words to finish the talk, right? So now, questions. Raise your hands and I will... Oh, there's lots of questions. I like that. Okay, I think you were quickest.
Okay, thanks. So, a great talk. Oh, I need to get closer. Okay, so great talk. Thanks, Fred. But you basically, if I may summarize it, you basically said you afforded zero trust on your servers by entrusting a ton in that config provisioning server. You were relatively sparse on how you ensured that that does not become compromised. Could you maybe talk a bit more about that?
Yeah, that's an excellent question, and right to the point. This is extremely problematic, right? Chain of trust and a root of trust control. In the end, we need to provision that at some point. We started with, we call it the bootstrap server, and at that point, all the configuration is lying around. There's also no SSH access, so we provision that one with the cloud interface at first, or if we are in the data center, we can do this just by plugging in the network. And in the end, we just lock it up. This is the way we do it, and yes, technically it's possible, right, that there's some issue with that. It's minimized because there's a very little time frame where somebody could maybe get access there, but it's something that you can circumvent. There's ideas to lock this up even more. At the time, there was no proper time to discuss stuff like TPM, hardware modules that lock this up with key management and stuff like that. This is, I would say, in the works.
So I have 2 questions. First, thank you for the presentation and the exhortation to actually do this. This is very nice. So you mentioned boot over network. Pixie is, of course, famously unsafe. So what are you using for a network boot? And you mentioned that you just switching the servers on and off, so you have some kind of IPME access. And how do you secure that?
Valhino, network boot.
What's then the infrastructure?
The first point, yes. You need there a strictly network management so that nobody can access this PXE line. So that means we have our own physics there and our own separation of the network zone, because it's really important, because there is no secure way you can do this. There was an idea to have it like with TPM modules and secure boot. It's theoretically doable, but from practical point, not. That's the problem there, because then if you have an incident or something else, you have thousands of servers, and then you have to see about a new key in the TPM module. Then someone has to go to the data center, has with the USB stick, change thousands of TPM modules that you can operate your system back. And then explain to your customer, sorry, it takes 1 week that the service comes back because of security. So that's a problem. That's why we can only achieve that by really network isolation, and nobody has access. So also the bootstrap machine, nobody has access from our employees. So we cannot have to and the network itself, it's our own separation of the network, and it's divided from the rest, so that also no other services can connect in, and then you can achieve this. Because PXE, of course, it's unencrypted, it's easy to attack, but there is no secure boot possible.
We do use HTTPS boot, though.
HTTPS is there, so this working, yeah, thanks. It was not in the beginning, but there's on the boards we can also use some chips there to use the PXE over HTTPS. But anyways, it's attackable, but this is the only way how you can reach that.
I saw you use Keycloak on your control plane, and I assume you use it to authenticate also to the control plane. a cluster, how do you do bootstrap and how do you avoid locking up your cluster if something goes wrong with a key cloak?
So we actually do not yet use Keycloak for authenticating against the Kubernetes API server. So,
Yeah. It's just maybe here in the Kubernetes API, the people don't have access and productive. So in the high secure Kubernetes cluster where we operate the customer data, there is no Kubernetes access. There's no kubectl.
So
There's no write access.
this will
Just
be
read,
annexed.
but there's no way to do K9S and change your cluster or something else. It's not possible there. Because it's this you cannot harden. If you give someone Kubernetes admin, then it's gone. So
Also, the config there is mostly infrastructure as code, right? So Keycloak itself is filled by crossplane. So everything lives in a Git repository. If Keycloak, dies for some reason, it's not nice. We lose access for a little while, and that doesn't change the fact that the system is still running. But we just, reboot the server and restart it, and then it's there again. It's also basically a throwaway Keycloak.
it's just to add to Keycloak, it's also needed for the identity check for our employees because it's not inside the platform, comes from somewhere else, and then you need something to connect and check that it's real the employee that's logged in, and that's why Keycloak was used. So because there's other solutions out for just the use case with the crossplane, but for this interpolation with some identity provider from outside, it's needed to have some services like Open Connect.
Thanks for the talk. Very interesting. So one thing that you mentioned is because you don't have so much options to go into the system and try things out, you need to have good visibility. Do you have anything in place to prevent that your developers get too much visibility so that they just log out all the customer data or put out some metrics that reveal too much and give them too much information that they shouldn't have?
You want to
So is this about observability data generally? Okay, yeah, I mean, that's always an issue, right? So you have to enforce this somehow by policy also. So you cannot just say, okay, log everything and we'll take care of the rest. That's also not possible. So logs need to be on a low level. But other than that, I mean, the access to the observability stack, I think it wasn't shown, also lives in this shared central cluster that, basically the central control plane cluster where also crossplane lives. So the access there is relatively strict, but there's no control based on labels or something that, some people can only see this subset of labels that's not in place. And as far as we know, that was not required so far. Same with metrics. So the access there is relatively tight, I would say. In terms of locking ourselves out, I think that has never happened before.
No, just the operating people need access to the logs. Of course, what we do is we have analyzing and incidents always to remove critical stuff from logs. But just here, I also have the questions from auditors and why they can turn off the system. Yeah, because they turn on the system, and you cannot prevent this. You have people that theoretically can turn off our service, but we need them because if something happens, then we need them to turn on. So that's the same question here. So we can prevent, nobody can have access to logs, but then you don't need logs. So, and yeah, that's the only way you can go there.
Then I have a question. You mentioned all the nodes in the cluster bootstrap themselves from the same source. How do they then differentiate themselves from each other? Let's say one shouldn't have SSH, one can. One shouldn't have disk, and so on.
Yep. So basically, each server that boots has a serial ID. And during the boot, there is something called a matchbox service that we use for it that knows how to map the serial ID to the configuration. And the configuration has then the information in it. Is it a server from the stateless cluster, from the database cluster? And also it maps then to the ignition file, right? The ignition file has then the information in it. Okay, it's a stateless cluster, then the SSH access is disabled. Or it's a database cluster, then the disks need to be partitioned. Yeah.
And just also to add, if there's a failure happened, then we have the network segmentation. The server boots then as a different machine, but cannot connect because the network itself has also on the port security and says, okay, you cannot reach the cluster you want to join because you it's wrong configuration. So in the end, if the wrong configuration is on the machine, he cannot access the cluster because it's a different network.
I have a question, a legal question. Is there restrictions who may use this secure service? Because you showed in the beginning that not even the government can access data. Is
The
it
government
possible
cannot
that
access
government says you may not accept this customer because we don't
We
have
never
access?
had it, but that's why we have a chat in the application. We will not introduce more in this chat to be not marked as a communication platform, just as a file share platform, because if we be marked as a communication platform, it can happen that we get legal problems. And nowadays, you know this with US laws and EU laws, and then maybe they come and say, yeah, you need to add some in your encryption. But it was never happened now, so that's great. But we don't want to be a communication platform, because we also have fear about that, like 6 months in German, Vorratsdatenspeicherung. We don't want to be part of this.
I don't know, do we have remote questions? No? Any more questions in the room? Yes, we have more questions. Great.
This ignition system that you use for bootstrapping sounds like it runs in a really exotic environment in your Rammelmüller V. I could imagine similar configuration happening on the server where the boot image comes from, or after the kernel starts in process 1 before the traditional init, before handing over to a traditional init system. Do you know of any reasons why this system is built like it is?
Yeah. Well, you're right? So at some point, the configuration script needs to run. Right? The init Rammelmüller V is basically at the end of the init script, basically. So the boot process, at some point, there runs a script that sets up all the devices and everything, and at the end of that, ignition is run. And you could do a custom script there, and in fact, that was the legacy setup of Idgard. There was about 1,500 lines of bash that is a custom init script. I would not recommend using that. If you ask Matthias, who is also in the audience, we had a nice incident once because there was some regex in it, and it could support 9 files, but the 10th file didn't match the regex, and then we spent half a night to look for what could this be. So maintaining a custom init script is really something that you don't want to do. Ignition is basically taking away from that, and you have basically a standard solution with some things. The other option is you could run in the beginning of your boot service that basically configures, but how do you get the service there? So you have to build your own image, and we don't even do that. We just take the plain image that we signed and everything, and then we just add some configuration and put it. So we have minimal config overhead there. So it's actually quite nice.
I see there's more questions, but also there's the time. How are we on time? Do we?
It's 54.
Okay, we take this one quick question. Quick
All right,
answer.
sure.
I'm not sure if it's quick, but I wanted to ask, how do you, what do you do against supply chain? Because you're, of course, losing a lot of foreign software, and that may also be compromised. How do you account for that?
I think that's Valentino's turf.
Yeah, actually, there was like a spike session on that we want to address this, all of this. For example, using, I'm not sure how the tooling is again, but we did not have the time yet to think about it properly. So what we are doing now is like just having a strict lifecycle management of our services, so that we just lifecycle the services accordingly and manually check if there are some security vulnerabilities currently in all of the microservices that we use in our platform. But the end goal is that you have, again, some central point in your cluster that basically informs you about if there is a security vulnerability available, and then also gives you an estimate on it, how urgent it is to act here. But this is not something that we do have yet.
But we do make sure that we only deploy, with digests and stuff, so we don't make sure that we control the things that go into the cluster. So there's no zero control.
I think further questions and further insights can be gained in the break. Before we go into the break, I want to thank our speakers again with a big round of applause. And each of them gets a present. It's a thank you card, it's a AI-generated children's book, and a chocolate.
Ooh.
Thank you.